In an electrolytic cell, you're driving a non-spontaneous reaction by applying electrical energy. You can drive a non-spontaneous reaction of an ionic salt in two different ways. Those ions have to be separated and able to move. So you can have a molten salt, meaning you have a melted ionic salt. So it's in the liquid state, and so those ions are able to move. Or you can have an aqueous solution, meaning the water has pulled those ions apart and they're free to move. Them being free to move is key to being able to perform an electrolysis. Previously, we talked about molten salts, and in those cases, you're only talking about the different ions because, for example, if you had molten copper 2 chloride, then you would just have copper 2 ions and chloride ions available. But in our context, molten salts are really hard to come by because you have to heat the ionic salt to really, really high temperatures in order to melt it. An easier way to separate those ions is to make the solution aqueous. So if you have an aqueous solution, you have your ions, copper and chloride, but you would also have water. This is key because water then could participate in the oxidation reduction reactions instead of either of the ions. So if you want to know what would happen if you were to perform electrolysis in an aqueous cell, you have to consider every reaction that could happen at both electrodes. So, in the case of copper 2 chloride, let's look at what could happen at the cathode. Now, the cathode means that it is reduction. If you have copper 2 chloride, looks like this, and I think it's helpful to write its oxidation states. So, copper 2, we have a 2 plus, and chloride, we have a negative 1. Charge. If it's going to be reduced, that means it's gaining electrons. Which one is more likely to gain electrons? Something that's positive or something that's negative? The positive ion is more likely to gain electrons and go to its neutral state. So copper 2 is likely to gain electrons to become copper metal. Let's look at the anode here just for a second. We're going to look at the anode before we look at the water. What could possibly be oxidized? Remember, oxidized is the losing of electrons, and so the ion that has a negative charge is more likely to lose electrons. So here we could say the chloride ions are likely to lose their electrons and become chlorine gas. Now remember, chlorine is diatomic, so that's important here. And to balance this equation, we first have to make sure that the number of chlorine is the same. The oxygen and hydrogens aren't present, and so they're already balanced, and then we would add 2 electrons to this to make it balanced. So these are the two possible half reactions at the cathode and anode from the salt itself. But remember, this is aqueous, so we could also have water participating here. So we need to consider what would happen to water if it were reduced or if it were oxidized. Now in this one, like this, we broke them up into their ions and assigned them each to an electrode. But water isn't ionic. An aqueous salt is already split up and floating around as ions, but water is a molecule, so it has to stay together. Now I think it's important to look at the oxidation states of water, of the atoms in water, before deciding whether it will be reduced or oxidized. So hydrogen in water has a +1 oxidation state, and oxygen has a -2 oxidation state. Now remember, which one is more likely to be reduced is the positive ion. So in this case, hydrogen is the positive ion. It's more likely to be reduced, and so that hydrogen is going to go from a +1 charge to a neutral charge. So this could form hydrogen gas. We're going to come back and balance this in just a second. And then at the anode, for the oxidation, we could see oxygen becoming neutral by forming oxygen gas. Now you can balance these with the half reaction method that we learned at the beginning of this unit. So let's look at the anode first because that one's a little bit easier. First we need to balance everything except for oxygen and hydrogen. In this case we only have oxygen and hydrogen, so we move to the next step, which is to balance oxygen by adding water. So we have 2 oxygens on the product side, 1 oxygen on the reactant side, and so we can balance that by putting a 2 coefficient with the water. Then we need to balance the number of hydrogens by adding hydrogen ions. We need 4 hydrogen ions on the product side. And then lastly, we balance the electrons. We need 4 electrons over here to make sure we have the same charge on both sides of the reaction. So we balance that by the acidic method, and that makes perfect sense at the anode. Now at the cathode, I'm going to show you why. I'm going to walk you through it, but we're going to balance it by the basic method instead. It's all the same, right? We just add one extra step at the end for the basic method. So to balance the water reducing into hydrogen gas, we first need to make sure everything but hydrogen and oxygen is the same, which it is, because we only have hydrogen and oxygen present. Then we balance the oxygens by adding water. We need more oxygen on this side, and so we're going to add a water. Then we balance the hydrogens. We have 4 on the product side, 2 on the reactant side, so we need 2 more hydrogen ions. And then we balance the electrons. The reactant side needs to have 2 electrons to make the charge over here, the same as the charge on the product side. Then you cancel out everything that is the same, and here's where it becomes a problem. The water is the same on both sides, and now we have a reaction where water isn't present. The problem with that is that this is supposed to be the reduction of water, so water needs to be present in the reaction. And so that's why we're going to balance this by the basic method. Now remember, in the basic method we're going to add hydroxides, the number of hydroxides as you have hydrogen ions, to both sides of the equation. And then you can combine the hydrogen ions with the hydroxide ions to get water. So I'm going to rewrite this here. This means we have 2 waters, 2 hydrogen ions plus 2 hydroxide ions gives us 2 waters plus 2 electrons to give us hydrogen gas and 2 hydroxide ions. So this is reduction of water into hydrogen gas. And this also could possibly happen at the cathode. If that balancing of those half reactions, that's a really important skill, let me stress that, but if that's really overwhelming in the heat of the moment, you can also find those reactions on your reference sheet. Now, be careful because hydrogen, oxygen, water, they appear a lot on here, but we knew right from the get-go that we needed water to turn into oxygen, right? So if we go over here, we can find water turning into oxygen, and then that shows you the rest of the reaction. We need those 4 hydrogen ions and those 4 electrons, which we found by balancing it here. Up here, we knew that we needed water to turn into hydrogen gas, and we can find that reaction here. Now again, you have to be really careful. I'm finding them really quickly because I know where they are, but you have to be really careful to find the correct one. And here you can see the water turning into the hydrogen, and it's the exact same reaction that we found by balancing with the basic method. I'm going to rewrite this cathode on another page to give us a little more space. Okay, so here is our potential reactions at the cathode. So the 2 things that could possibly be reduced were the copper ion and the water. To find out which one is actually reduced, we want to look at the electrode potentials. The electrode potentials tell us which one is more likely to be reduced. If you think of it as like a tub, you are filling it with water, and if you leave the water on, most tubs have like an extra drain towards the top, and so you could potentially fill your tub up, it would spill over onto your bathroom, or as it's filling up, it could like drain into that safety drain. And it's similar to these reactions where whichever one has the lower potential, that one is going to be the one that is reduced because it takes all of the energy and it never builds up enough energy in order to reduce the other one. So you find your 2 reactions. We said we had copper 2 becoming copper solid is a potential reduction, and we also said that water becoming hydrogen is a potential reduction. So for the copper, the potential reduction is 0.34 volts, and for the water, the potential reduction is negative 0.83 volts. Whichever one of these is more positive is the one that's going to be reduced. Remember, positive means that it is spontaneous, right? So the closer it is to being positive, the easier it is to reduce. So the one that's more positive is the one that will be reduced. So in this case, we would see copper ions turning into copper metal, and we would not see water turning into hydrogen gas. Let's do the same thing for the possible reactions happening at the anode. Okay, so these are the possible reactions we decided that could happen at our anode. To determine which one actually happens, we go to our reference sheet, and we're looking for chloride turning into chlorine. You can find this here, but notice that this reaction is written backwards, and then the other one is here, which is also written backwards. If the reactions are being oxidized, right, they're going to be written backwards on the reduction potential reference sheet. So we're going to take these standard potentials for the electrodes, and we're going to reverse the sign. This means for chlorine, our electrode potential is negative 1.36 volts, and for water, our electrode potential is negative 1.23 volts. We're going to follow the same rule as we did before. Whichever one of these is more positive is more likely to occur. So we see that the water turning into oxygen is more positive, and so this is the reaction that we'll actually see. Now be really, really careful because these are standard reduction potentials. Standard means at 25 degrees Celsius and with a 1 molar solution. So this solution is 1 molar chloride ions. We would see the oxidation of the water instead of the chloride. But if you had a more concentrated solution, you're no longer at standard conditions, and you very well may see the chloride being reduced instead of the water. So please don't try this at home, because if that happened, look what you're creating, chlorine gas. So you're predicting that at standard conditions, the water would turn into oxygen instead of the chloride turning into chlorine. So if we want to write the overall reaction equation, we can combine the two half reactions that we've selected at each anode. These are the two reactions we said were more likely to happen, or that we would see actually happen. To write the overall reaction, this is just like at the beginning where we're balancing by the half reaction methods. And we first need to make sure that the number of electrons is the same in both equations. Since it's not, we need to multiply this one by 2 so that we have the same number of electrons being given and being taken in our reaction. Remember, that does not affect the electrode potentials. Then we can combine them together, so everything on the reactant side goes on the reactant side of our overall equation. So we have 2 copper ions and 2 water molecules reacting to form everything that's on the product side. So we have 2 copper atom metal, an oxygen gas, 4 hydrogen ions being formed. You can always double check your work. Everything should already be balanced. If it's not balanced, then you've done something wrong. Okay, so we have 2 coppers on both sides of the reaction. We have 4 hydrogens on both sides of the reaction. We have 2 oxygens on both sides. Another way you can double check is make sure the charges cancel. So over here we have 2 times 2 plus, so we have a 4 plus charge on this side of the reaction, and we have a 4 plus charge on this side of the reaction. So everything is canceling, and we can be confident that we've written at least a correct equation. So this is the reaction that would actually happen in your electrolytic cell. To find the cell potential, we just add our electrode potentials, and we would get negative 0.89 volts. We always ask ourselves, does that make sense? And the fact that this is negative is really important. This is an electrochemical cell. An electrochemical cell means you're applying electric energy in order to drive a chemical reaction, which means our E cell should be negative because it's a non-spontaneous process. So that's a really good sign that we've done this correctly. And lastly, let's just talk about what you would see if you were actually doing this reaction. So copper 2 ions are blue, so you would have a bright blue solution. If you think of like a pool with that bright blue color, that's what that would look like. And that blue would slowly start to fade, and you would see like something the color of pennies, an actual metal starting to plate onto your electrode. So your electrode would be turning like a pink copper color, and then your water would be turning into oxygen gas. So that oxygen is being oxidized, right? So it's happening at the anode. So at the anode, you would see it start to bubble. Remember, in an electrolytic cell, the anode has a positive sign. So whichever electrode you connected to the positive side of your battery would start to bubble. Now that's different because in a galvanic cell, the positive sign goes with the cathode, but it's reversed for the electrochemical cell. So the positive sign would be on the anode, and you would see gas starting to bubble out at the anode. And the pH of your solution would start to decrease pretty dramatically because you're adding a lot of hydrogen ions. So if you were to actually run this experiment, that's what you would see. You would have a cell potential of negative 0.89 volts. And I know this is a lot. I know this is a lot, but this is kind of like the pinnacle of everything you learned about electrochemistry we're applying here. So this is a really, really important concept. I know it's a lot of work, but you can do it.